Welcome everyone to the Batavia Lyceum Association. I'd like to thank Ryan and Melissa for hosting here at Sidecar Supper Club. We do this once a month, the second Monday of every month. I believe this is our fifth. I can't remember off the top of my head. What else am I forgetting? I don't remember. Oh yeah, we kindly ask for a $5 suggested donation. All the money goes in to pay the speaker stipend. So that way we can thank them for their efforts and their time. Every one of our speakers is diligently working academically to come up with a topic for us every month. And we are very thankful for what they do. Personally, this speaker is one of the best people I know. I've known Mark since, as long as I've known Nick as well. I met Mark at the same event that I met Nick. It was at the First Congregational Church, the first time that the bookshop actually sold books inside of a place.
I bought some.
Yes. And I've come to know Mark and his lovely wife Cindy. They're dear friends of mine. Mark, when he shows up every Sunday, it is truly one of the better experiences of my week. Our conversations are lengthy and energetic, and I'm always learning something new from Mark. And I know that you will too tonight. So once again, please give it up for Mark.
Thank you all for coming tonight. I understand that there might be a football game that we're up against. Or Batavia Bulldogs. Anyway, I'm glad that you guys are here. I hope this will be an interesting topic for you. This is kind of a personal talk for me. I wanted to talk about this for a very long time, and I'm very happy that the Lyceum has given me the opportunity and the stage at which I can talk about this. My degree is in nuclear physics from Northwestern University, and for many, many years, I was counting back about 45 years, the nuclear physics community has seen a lot of funding going into the fusion energy program, and the non-fusion part of nuclear physics has sort of gotten just the scraps that are left over from our fusion energy funding. And so I've always had a great deal of jealousy of people that were working in this area. But I've learned many things in researching this topic. There's been a lot of changes since I first started learning about fusion energy and learning about the programs that the US and other countries are running. So we'll talk about all that now. Come on. Hello. All right.
No, now you lost it.
No. There we go. So, if you were here for my last talk for the Lyceum, I talked about the Permian extinction and global climate change and the very real, in my opinion, possibility that the human race will go extinct from climate change within 100 to a few thousand years. But hopefully, technologies like fusion energy can help us avoid that kind of calamity. But go back to the topic of greenhouse gas emissions for just a minute. You can see on this slide that fully 25% of the greenhouse gas emissions in the United States are originated from generating electrical power. So if we had cleaner ways of generating electrical power, that would be a big improvement in our situation with respect to climate change. Also, the other industries that you see there could benefit by switching from sources of energy that generate pollutants, that generate greenhouse gases, to a more electric-based economy, provided, of course, that the technology that replaces burning coal, burning oil, and so on, is cleaner than those types of fuels. Even if we look at where electricity is being used, I mean, we talk a lot about electric cars, putting solar panels on our house, and so on. And even those generate greenhouse gas emissions. It's, in the manufacturer of the solar panels, manufacturer of automobiles, for instance, a clean electric powered automobile still has to be made out of steel and plastic and other things which lead to greenhouse gas emissions. All right, so where do we actually get our energy from in this country? Well, 88% of the energy produced in the United States comes from burning things. So here is a power plant. I'm not sure if this is a gas-fired or coal power plant. I don't see any huge piles of coal, so I suspect this is a gas power plant. And of course, these are major sources of greenhouse gases. We of course get our electricity from Prairie State Coal Plant, which is not considered to be very clean energy. It's certainly not renewable and not sustainable. But the important point here is that the vast majority of our energy comes from burning things. About 8% of our energy comes from nuclear power plants. Currently, there are 90-something nuclear power plants in operation in the United States. Many of those are starting to reach end of life and are going to be decommissioned. And by the way, decommissioning is a very long process that takes decades to complete. But something's going to have to replace that power eventually. About 4% of our power currently comes from wind farms. Another 2% from hydroelectric power dams, both large and small. 2% from solar power, and much less than 1% from geothermal. There's very little geothermal power production in the United States. Here is for those who prefer pie charts, two nice pictures. Here's a breakdown of where our energy comes from. It's interesting because they have lumped into renewable energy, biomass, biofuels, and wood, which I have taken out of green energies because you're still burning something. So I've lumped them in with coal, oil, and natural gas. I also learned a new unit of energy in doing this research. It turns out there is an energy unit called the quad. The quad is 1 followed by 12 zeros, British thermal units. So 1 quadrillion British thermal units. The total energy consumption in the United States in 2022 was 100 of those. Later in this talk, I'm going to be using the unit joules rather than quads or megawatt hours. So that's roughly 1 quintillion joules. That's 1 followed by 15 zeros. Or 294, let's say 300 million megawatt hours. I think it's good to appreciate too the extent to which the United States has an infrastructure for distributing both the energy inputs, the fuels that we need to produce energy, as well as the energy output, which is primarily, for these purposes, electrical. So we have over 300,000 miles of natural gas pipelines. We have 200,000 miles of high voltage lines. This one is, I think, the important one because any replacement for electric energy production is going to have to reuse this infrastructure. We have 190,000 miles of oil pipelines to deliver not just gasoline, but other uses for oil. And 140,000 miles of freight rail lines for hauling coal, tanker cars of oil, whatever else goes in here. Now, there are some interesting new technologies coming down the road for cleaner energy production, cleaner than burning things. One of the very promising ones is hydrogen fuel cell technology. So hydrogen fuel cells, you take a supply of hydrogen. Here we are, over here. These are the fuel cells. You put hydrogen and oxygen into the fuel cell. There's a catalyst in the fuel cell. The hydrogen combines with the oxygen to produce water and electricity. So you siphon the electricity off, the byproduct is completely clean, it's just water. If there's a problem here, it's where you get the hydrogen from. If the hydrogen comes from electrolysis of seawater, which is commonly the case, you're still using electricity to break up the oxygen and hydrogen from the seawater. This has also been touted as a replacement for electric cars, lithium batteries in electric cars. One problem though is that many people do not like driving around with the equivalent of the Hindenburg strapped underneath their car. So there is an issue of making sure that this is very safe. You do end up with a high pressure tank of hydrogen as your fuel when you drive around with a hydrogen car. Another really cool idea, one that I like a lot, by the way, being a nuclear physicist, is the idea of small modular nuclear reactors. Okay, so this is a small modular nuclear reactor. They're clean, well, they may or may not be cleaner than the reactors that we've been building for the last 40 or 50 years, but they are, I believe, safer because the modularity means that, first of all, they're small reactors. So you build several of these to produce the amount of energy that you need. So the idea is you would build one of these to power a city, back here, or you would build one of these to even maybe power a neighborhood of a city, or a manufacturing plant. And again, because they're standardized, you build them all the same, and therefore you can build them safely because you hopefully end up with a proven design that you just stamp out one after another. I think this is a great picture, by the way. I think this is some Westinghouse propaganda because they're being very politically correct, because here you can see they've included solar cells, and way in the back, hard to see, but there's a wind farm, okay? So they're pushing the idea of small modular reactors are as green as these other sources of energy. Unfortunately, a lot of people, especially in the United States, have a hard time accepting whether nuclear power can be made safe enough to grant more licenses. I believe the first license to build a new nuclear power plant in many decades was only recently issued, and at that it will probably take 20 to 30 years before it becomes operational because of all the administrative hoops that we have to jump through. Okay, and then finally, we're going to come to the topic of today's presentation, which is fusion energy. So this is a fusion energy reactor seen from the inside. And I'm going to show you how these things work, what fuels they use, what they produce in terms of byproducts, and so on. And I'm going to give you a trigger warning right now. There is some simple math coming, nothing more complicated than fractions, although I know some have trouble even with fractions. There is a minor amount of physics involved, and I am going to be using metric units. So here's your very, very quick course on how much nuclear physics you have to know to understand how fusion power works. And the great courses, by the way, are wonderful courses, so if you really do want to learn something about nuclear physics or many other topics, they're not sponsoring you, okay? They do have those courses, yes?
I think they have a new name, Wondrium.
Wondrium, yes,
Yes.
yeah. I'm always confused because I see both great courses in Wondrium, and I know that Wondrium includes the great courses as well as some other channels, So let's start first by understanding how a fission reactor works and why they're considered, more evil than a fusion reactor. So fission reactor works by having uranium fuel, okay? Uranium fuel, if a neutron hits it, uranium is unstable when you add a neutron, and that uranium will split or fission into two or more byproducts. So in this case, the uranium is split into cesium-140 and rubidium-94, and is kicked out a couple of neutrons and some energy. So it's that energy here that we want to capture in a nuclear reactor to make electricity. How is that done? Well, here's a schematic of how a nuclear fission reactor actually works. So here is the containment vessel, which has the core of uranium fuel inside of it, control rods to control the intensity of the reactions going on. But in the core, you heat a fluid, typically water, which then goes, the hot water goes to a steam generator. This is a closed loop so that none of this radioactive water escapes. But in the steam generator, you heat cold water to make steam. The steam runs through a turbine, connected to an electric generator, which goes out to the power. The leftover steam goes into a condenser where the cold water loop circulates to remove the heat from the steam, turn it back into water, and it gets pumped back into the. Can y'all still hear me okay? Okay. All right. So that's how a fission nuclear power plant works. Remember this diagram because we'll compare it to some other things later. A fusion reaction or a fusion reactor works in a completely different way. Instead of splitting atoms, it combines atoms. It combines nuclei, I suppose I should say, to be most correct. So in a fusion energy, you have two small nuclei, and these are isotopes of hydrogen. So deuterium, hydrogen is one proton, no neutrons, H1. Deuterium is a proton plus an extra neutron, so it's atomic number 2. And then tritium, which is a proton and 2 neutrons. These are all forms of hydrogen isotopes. You take the deuterium and the tritium, you combine them under tremendous pressures and temperatures, and what you get out is helium, perfectly clean. You get some energy out, and you get a neutron out, because helium doesn't like to have that extra neutron, so it gets kicked out of the reaction. Now on this side, we've seen that you can use deuterium and tritium as fuel in a fusion reactor. You can use other things as fuel. In principle, you can use straight up hydrogen as the fuel, or straight up deuterium. But the problem is that to use deuterium plus deuterium as the fuel requires much higher temperatures and pressures than if you put tritium in things. You can also use, I think, boron and a few other elements as part of the fusion reaction. But so far, deuterium plus tritium seems to be the most effective. Deuterium, I will talk about. Deuterium, so the unlimited energy part of this is that deuterium is very plentiful. You get it from seawater. I think something like 20% of water molecules in this ocean are actually heavy water with deuterium. So all you have to do is extract the deuterium from seawater, and you've got all you might want to ever have. Tritium is a different story, and I will come back to that story in a later slide. Okay? So fusion reactions are how the sun gets its power. Ultimately, the sun is where we get all of our power. It's the tremendous gravity of the sun that causes or allows the fusion reaction to take place and be self-sustaining. We are able to do fusion reactions here on Earth, actually relatively easily, because all you really need to do is take some deuterium and tritium and wrap a fission bomb around them, and you can get the fusion to go off and release a tremendous amount of energy. But that's probably not what we want to do to generate electric power. So how do you generate electric power from fusion reactions and do it in a controlled and safe way? Well, it's not this. So there are basically two main approaches to how you generate fusion power. The first of these, and I'm going to talk about, is the magnetic confinement reactor. And this is a schematic of a magnetic confinement reactor. In a magnetic confinement reactor, you have a plasma that consists of deuterium and tritium fuel. Plasma means that the fuel has been heated to such a temperature that the electrons are no longer bound to nuclei, and they do their own thing. But the fact that this is a plasma means that you can wrap coils around this, quite complicated coils as it turns out, and use a magnetic field generated by those coils to compress that plasma, and if you compress it enough, you get a fusion reaction. So that's the basic principle of how a magnetic confinement reactor works, right? Here is a schematic of how you would use a confinement reactor to generate electricity. So down in the lower left corner, you see we have a supply of fuel. We have a way of heating the supply of fuel to generate the plasma. The plasma swirls around inside this containment vessel with a variety of magnetic coils around it to guide it and compress it. As the fusion reaction takes place, remember the spare neutron that gets kicked out? It's the neutrons in a fusion reaction that actually generate the heat that you need to eventually generate electricity. So these neutrons get kicked out, they hit the wall of the containment vessel, heat the containment vessel, you surround the containment vessel with a jacket of cooling liquid, okay? So effectively, you're heating the cooling liquid, you pump the heated liquid out, put it in a steam generator where you generate steam, it goes through a turbine, generates power, and comes out into the electrical grid. All of this side should look familiar already, okay? The cooling fluid goes back into the jacket. These machines tend to be a little bit complicated to build. This is the joint European torus. There is a guy somewhere in the picture. Oh, there we are. So there's two little men standing down here. And miles and miles of piping, coils, cryogenics, all sorts of cool stuff. This is a more schematic view of it. You can see all the different layers that are involved, the huge structure that's needed to maintain the sort of rigidity of this due to the high magnetic fields. Here's our guy for scale. Okay. The jet began construction in, I think, late 1980s, and is now was slated, I haven't checked to make sure it actually was decommissioned, but was slated to be decommissioned last month. Jet never produced any electricity, just so you know. The other approach to this is what's called the inertial confinement reactor or the laser confinement reactor. In this method, you have a pellet of fuel. So that little BB-sized thing there contains deuterium and tritium and some ceramics and some other complicated stuff that goes together. It's held in place. You shoot really incredibly intense laser beams at the pellet. There's actually two ways of doing this. You can shoot the laser beams directly at the pellet and use the compression of the laser beams alone to compress the pellet and cause the fusion reaction to occur. But more commonly, the approach now seems to be to use a special, essentially a jacket around this pellet and use the laser beams to generate incredibly intense X-rays, which then are directed at the pellet to compress it and cause the fusion reaction to occur. Here again is a schematic of a laser confinement power plant. Again, you will notice that everything on this side is exactly the same as probably even a coal-fired plant. The only difference is how you generate the heat and what you have to inject to cause the fusion reaction to happen. This is a very simple diagram because it shows only 4 lasers. You'll see in the next slide that it's a little more complicated than this. The other thing I noticed in this schematic is that they're not using water to circulate within the confinement. They're using a molten salt, probably, what are they using here? Might be boron. So this is the National Ignition Facility at Lawrence Livermore Lab out in California. This blue thing here is the target chamber. I believe these are the lasers directed into the target chamber. This thing has 192 lasers. US has been working on all these projects for a long time. I mentioned that JET started in the 1980s. I think NIF started maybe in the early 1990s with the design work. It's actually been doing experiments for close to 20 years now. I found a really cool paper by a student at Stanford who looked at the expenditures in the United States for fusion energy from the very conception through to 2021. This is all normalized to 2021 dollars. So in total, we've spent $36 billion 2021 dollars over 7 decades to fund nuclear research. And you can see that the funding profile is very up and down. There was sort of a small baseline going on up until the mid-70s, then a huge jump in the mid-70s, which then tapered off to the 80s and 90s. You might think that might be because Congress wasn't seeing results, which is probably true. And what looks like an uptick, well, fairly steady through the 2010s, and now we're going to see an uptick because of some recent announcements that have been made of breakthroughs in fusion energy. This red line down here is shown separately because that is U.S. contributions to the International Thermonuclear Experimental Reactor, ITER. So fusion energy is promised to be safe, it's promised to be cheap, it's promised to be clean, and it's promised to be unlimited. So is that really the case, or is there a little bit of hype involved? Back in the 70s, again, this goes back to when I was a grad student, and I had to fly for my thesis advisor to deliver some piece of equipment back to the manufacturer. And when I got to the airport, you've seen Airplane, there's the scene where I forget which character it is, but he's being pursued through the airport by the Hare Krishnas. And the Hare Krishnas were, of course, in the airport, but there was another sort of fringe group in the airport, and that was the Fusion Energy Foundation. Okay, they had their little booth set up, and they were stopping people, talking to them about the wonders of fusion energy and how we should all support it. A political side note is the Fusion Energy Foundation was headed or founded by Lyndon LaRouche, who is a famous conservative who ran for president a couple of times in I think a third party, never got any traction, but fusion energy was his baby. So in 1979, October of 1979, Fusion Energy Foundation was actually predicting that by the 1990s, we would have fusion energy, we would have practical fusion energy. Well, I think missed that by a little ways. And as you read through, there's actually a joke that, that fusion energy is 30 years away and always will be. And that's it's becoming less true, I have to say. This is becoming less true. But if you look at the history of fusion energy, this is pretty much the history. Another study I found, I think this might have even been from the Smithsonian website. Oh no, I'm sorry, Scientific American. Did a survey of literature and looked at, by year, okay, so from 1980 through 2020, in what year did scientists and futurists predict that we would have fusion power? Okay, so there's actually two sets of data here. The blue line, or the blue data points, are the prediction for when we would have fusion energy demonstrated, and the red line is when fusion energy would actually be practical for producing electrical power. And you can see that even up until practically today, the predictions for commercialization of nuclear fusion energy have ranged at about the 30-year or more, this is 50 years up here, mark, even up until 2020, 2021. There is a slight downward arc on both of these data points, and again, that comes back to some of the recent developments. I was very surprised to find out that there are actually, so the International Atomic Energy Agency, IAEA, does a yearly review of fusion energy devices around the world. There are currently 91 fusion energy devices in operation. I might have lied earlier when I said that there were 91 nuclear reactors. I think it was actually 93. But there are 91 fusion devices in operation. 29 countries have already in operation or are in the process of building or are planning to build fusion devices. And there's some, you can see that the big countries are certainly there. Here's us, Russia, China, the EU, individual countries in the EU anyway. Some up and coming, I should include Australia in that, some up and coming wannabe First Nations, Brazil, India, and then some interesting countries which I did not at all expect. So Egypt, Libya, Iran, of course, Pakistan, because I think they want to keep up with India, Thailand, I can't quite wrap my head around Thailand, fusion energy program, and little tiny Costa Rica.
What's the little red dot to the east of Haiti?
To the east of Haiti, I think that's whatever island is part of the Netherlands. Just like Greenland does not have its own fusion energy project, it's part of Denmark.
I was wondering like that.
It was too common. Oh, and yeah, I forgot to mention South Korea in that top tier. So they're in there too, as well as Japan. Okay, so there's work being done, a lot of work being done. Let's talk about some recent developments and some facilities that show a lot of promise, but also have their issues. So we'll talk first about the National Ignition Facility. I showed this picture earlier. The National Ignition Facility is funded completely by the U.S. Department of Energy, at least I believe that's the case. So it's all a U.S. endeavor. I did mention that when you looked at that first picture, the containment vessel was that little blue thing. So that's this right here. And all the rest of this are the lasers and the pieces you need to generate the lasers. So this is pretty ambitious. And like I say, they've been working on it for actually decades. But there was big news in December of 2022, and additional big news in, I think, June of 2023. But in 2022, it hit the news that we were a step closer to nuclear fusion energy. Why? Because the NIF finally produced more energy out of a fusion reaction than they put into it. So break even, at least that's what they were told. Okay, Livermore scientists should experiment with the stored breakthrough. Fusion breakthrough, inflection point for clean fuel technology. U.S. announces breakthrough. Fusion breakthrough, big leaps yet to come, scientifically huge. World record fusion experiment, produced even more energy than expected. Energy Secretary announces tremendous scientific breakthrough. Breakthrough fusion energy blast, New York Times. Nuclear fission breakthrough proves clean energy future is possible. So everybody was really worked up about this. We finally made this breakthrough. Great, the end is in sight. Everything's going to be good. Here's our little bit of math. So physicists define a quantity called Q to quantify the efficiency of energy production. So Q is defined as the amount of energy that you get out of a reaction divided by the amount of energy that you put into that reaction to cause it to happen. So Q equals 1 is called the break-even, so you get as much energy out as you put in. That's okay, that's good. Q greater than 1 means that you've produced more energy than you put into it. And that's what we're after, is to produce more energy, because remember, ultimately we want to generate electricity out of this. Okay? So back in December, the big news was that the NIF put 2.05 megajoules of energy into the target, and fusion happened, and we got 3.15 megajoules of energy out. Yay. So if you crank the number, you get Q of 1.5, which is not bad. In fact, it's pretty good. So mission accomplished, right? We're all done. We can pat ourselves on the back, hand up. Well, I don't think you get Nobel prizes for that. Okay, we'll hand out a bunch of patents. Okay. However, so if you look more closely, you find out, that red is hard to read, I'm sorry. You find out that the energy that was put in, the 2.05 megajoules that everyone is quoting, is just the energy delivered to the target by the lasers, okay? It doesn't include any of the energy required to charge those lasers to cause them to fire, or any energy required for running cryogenics, or anything else that is involved in this process, including the lights in the building. And you dig around in the more skeptical literature a little bit, and you find the quote that the ignition facility draws 300 megajoules of energy from the grid for every shot. And by the way, it's weeks between each shot. So the other thing is, remember, we're trying to generate electricity, and we know from nuclear power plants and coal-fired power plants and so on, that the efficiency of generating steam, running a generator, and turning that into electricity is about 33%. So what comes out of the reactor, about 33% of that actually goes into the electrical grid. So we have to take that into account as well. So if we re-crank the numbers with these more realistic numbers, suddenly things don't look so great. We've got a third of 315 megajoules is the energy out to the electrical grid. We have 300 megajoules of energy in, and you get a Q of 3,000.
0.003.
I talked a little bit about the fuel that's required in a laser reactor. So this is actually the fuel pellet right here. It's about the size of a BB maybe, or a small bead. It goes inside this cylinder, and that cylinder goes inside this target holder. All of these components, the bead and the cylinder, are complicated to manufacture. They have to be done to high tolerances. They have exotic materials in them. The bead requires cryogenics because you're dealing with deuterium and tritium gases, and so on. And so this is not at all like shoveling coal into a boiler. You're not going to be shoveling these things in, 10,000 liters. So that's another drawback of this method. So let's turn to the latest developments in the other method, the magnetic confinement. So we will look at the International Thermonuclear Experimental Reactor, ITER. And because physicists have no lack of hubris, someone realized that ITER is also the Latin word for the way or the journey. So officially, ITER is the way. It's not the International Thermonuclear Experimental Reactor anymore. Okay. So this is ITER under construction. It's being built in southern France. Again, for scale, you can barely see, but there's two people standing here. Okay. I don't think I found any other people in this one. Is there a guy down here somewhere? Oh, no, I think that's a small crane or something. So it's under construction. It's been under construction actually for decades. Okay. ITER is officially a partnership or collaboration, or I forget the word they use, of 7 entities. You can see their flags here in very politically correct alphabetical order. You got China, European Union, India, Japan, South Korea, Russia, the United States. I thought it was kind of funny, in fact, that they left 2 empty flagpoles in case somebody still wants to join. And then I'm assuming that this is the ITER flag over here, but I don't know for sure. It could be Azerbaijan or somebody else. So those are the main sources of funding for the ITER project. Each nation is committed to providing a certain level of funding or a certain level of work in kind for building this reactor. There are 35 other countries that the ITER website says are part of the collaboration, but I can find nowhere on their website where it says who those 35 countries are or what they're doing. And you will of course notice that at least 3 of those countries are kind of questionable partners as far as the United States is concerned. China, India is still kind of okay, although when I worked at Fermi, they had a great deal of paranoia about whether the Indian collaborators were going to be stealing our secrets, which we had none of anyway. And then of course Russia. So here's a cutaway view of the ITER reactor. So again, you can get kind of a sense of the complication involved here. You can see the purple plasma whirling around inside, the various coils, the jackets that surround the containment vessel. This thing is 1, 2, 3, 4, 5, 6 stories high. And the construction covers a massive area. I believe what we were just looking at is inside this building, but I don't know for sure. Again, it's nicely politically correct of them to have a solar farm. I assume that's the power of their administrative domains. If you look carefully, you'll see that there's a big power substation back here. And spoiler alert, that is not for all of the power that ITER is generating. Okay. So ITER quotes in all of the literature, the director has come out several times and said very confidently that they will achieve a Q of 10, that they will put 50 megajoules into the plasma and they will get 500 megajoules out. It's a good goal. But again, the 50 megajoules going in is just what they're using to cause the plasma itself to fuse. It's not running any of the peripheral systems, it's not maintaining magnetic fields, none of that kind of stuff. And this doesn't involve cryogenics as well. So again, I found the statement similar to NIF. ITER draws about 300 to 400 megajoules of energy from the grid in order to maintain fusion. And we have the same 0.33 efficiency in producing electricity. So ITER's 10 becomes roughly half, which is still a lot better than NIF, but it's a long way from a practical power plant. And if only that were the worst news. So just very recently, in June and July in fact, there was a bunch of headlines about ITER being in trouble. For one thing, their director died unexpectedly, which was unfortunate and tragic. But there were a variety of other problems as well. Cracked components. They had installed probably miles of cryogenic tubing, which required very careful welding. Another contractor came in and cleaned the tubing and used an acid that degraded the welds. So that all has to be redone. The containment vessel itself has these large fabrications that are meters tall, but they have to assemble with less than sub-millimeter precision. Well, when they got delivered, they found out it didn't fit, so it has to be done more. The really big news out of this, I suppose. Well, I wanted to mention one more thing because it will come in later in the discussion of how safe fusion energy is. Another issue that they had was that the subcontractor who was doing welding for some part of the reactor was supposed to provide and was contractually obligated to provide welders that were certified to work on welding in nuclear power plants. That's a very specific certification and level of quality and skill that's involved there. And they said, yep, no worries. But of course, they later found out that, nope, those guys didn't have that certification. So all of those wells are gonna have to at least be inspected and potentially all redone if they don't fit standards. So the interesting thing is that Eater's administration does not even attempt to predict when Eater will be operational or how much it's actually gonna cost. This is the history of predictions by year of when Eater might become operational. And way back in 2006, when they started construction, I guess is that 2006? Yeah.
Yeah.
The prediction was 10 years. And it stayed basically 10 years for many years. The budget was, I'm sorry, it's a small screen. $6.3 billion was the initial budget estimate, which I think is 5 billion euros, if I read that correctly. Well, here we are, what, 17 years later? And the last prediction was that it would be available in 2025, or would at least be operational in 2025, and the cost estimate had gone up to, geez, I should have your reading glasses.
You want mine, Mark?
Yeah, sure,
Okay.
but I think it's, this is some tens of billions of dollars, or of euros now. And then in 2023, you can see there is no timeline, there is no budget. They don't even expect to have a budget or a timeline for another year. So they're heavily on the rocks.
Mark, what was it you said I should get?
No, never mind.
Never mind. Shouldn't drink.
We said that fusion power is unlimited. Well, that turns out not really to be the case. Maybe it's unlimited, but maybe not. So deuterium is fine, we can get that from seawater, but it turns out that tritium is only commercially manufactured or created in industrial quantities in a certain kind of Canadian water-cooled reactor called the CANDU reactors, which only are in use in Canada and South Korea. And those reactors are now 30 years old, and they're slowly being decommissioned. Plus, let's not forget that tritium will decay relatively quickly. And so even if you stockpile a bunch of tritium for the future, it's not going to be there, 5 or 10 years from now when you think you might want to use it. Okay? So this is a prediction or historical trend plus prediction of the world's tritium supply. If ITER never turns on, it's still going to slowly decay. And if ITER turns on and uses the amount of tritium that they predict to use, 0.9 kilograms per year, then somewhere around the middle of 2050, the world's going to just run out of tritium, unless we find another way to meet it, which is likely to happen. There is a proposal that coating the inside of the containment vessel of the magnetic confinement reactor will generate tritium as a byproduct as it's being bombarded by the neutrons. And so maybe we can collect that tritium and then use it to refuel the reactor. But that's not been demonstrated yet. So. I think the good news for fusion energy is that there is an awful lot of interest in the private industry now in developing fusion reactors. They have certainly recognized that there's a lot of money that could be made if you can come up with a successful fusion reactor power plant. So I'm sure there's many, actually more than these, of companies that are working on fusion energy projects. These are just ones that happen to be on this slide. Of course, we've already seen that fusion energy projects are not at all cheap. And so this is the realm of billionaire investors to make this happen. But capitalism can make things work. The Department of Energy along with their budget request of $1 billion for 2024 for fusion energy, announced that they're making an award of a total of $48 million to these 8 companies in the United States to work on private fusion energy ventures. So even the energy department is diversifying its research. So, kind of in the end, is fusion energy safe? Well, it depends. I consider that fusion energy, like everything else that humans do, especially, dare I say, in our society, will be as safe as humans can make it while they're still making a profit. Okay? And we've already seen with ITER where contractors cut corners, hired the wrong kind of welders and so on. So I think there's plenty of chances for human error and for accidents to occur. Even if, now one thing that fusion reactors have going for them that make them much safer than fission reactors is there is no possibility of a runaway reaction. It's so hard to get that fusion reaction going and maintain it that if the facility lost power or anything else, even if it lost cooling, you shut down and immediately the reaction stops. It's not like a fission reactor where if you lose cooling water, those rods continue to generate heat, they melt down. That's been the basis of every fission reactor accident so far, going back to 3 Mile Island, Chernobyl, Fukushima. So it's relatively safe, I think, but I doubt that we can make anything completely safe. Is it cheap? No. That was an easy one to answer. You know, like back in the good old days of the 1950s and 60s when people were pushing nuclear reactors, you know, I remember, I was a young kid then, of course, but I still remember that people were saying that, oh, nuclear power would be so cheap they won't even bother to charge you for its use. And I think I've heard kind of similar things said about fusion power, and that's not the case. Is it clean? No. No. And the reason it's not clean is because you're still running a nuclear facility, and you may not have fission byproducts to get rid of, but you've got all the low-level radioactive wastes still to get rid of. And I have the question of what happens when you decommission a fusion reactor. You've been pumping neutrons into these containment walls for who knows how long, and I believe that those containment walls would be highly activated and would constitute high-level radioactive waste. Is it unlimited? Well, maybe. It depends on what technology you can do with developing tritium. Of course, there are also other proposals to use other elements for the reaction, but the problem is that deuterium and tritium are kind of a sweet spot. If you go too far into heavier elements, or if you go back to deuterium on deuterium, you have to achieve much higher pressures and temperatures to cause the fusion reaction to occur. I forgot one thing that my wife was supposed to remind me of, because I forgot all about it when I did my run-through with her. Going back to SAFE and recalling who some of our partners are in here, and recalling some of those countries that have projects ongoing, it turns out that fusion reactors are just great for producing weapons-grade plutonium. Because all you have to do is take uranium, stick it inside the fusion reactor, wait a couple of weeks, it gets bombarded by neutrons. The neutrons go through a couple of reactions inside the uranium atoms, and what you end up with is plutonium. You build uranium plus a neutron goes to neptunium plus a neutron goes to plutonium. So you can make all the plutonium you want, basically, as long as you have uranium. And so try policing that. All right, so.
1.21 gigawatts.
We are quite a ways away from putting Mr. Fusions in the back of our cars and eliminating all of our energy needs and replacing them. So I have a ton of references, I'm not gonna expect anybody to write all these down, but if you want this URL, if you wanna either write it down or if you wanna send me an email, oh, I should have put my email address on here. I've been posting my slides to this URL, so you can see not only the fusion energy talk, but I have the slides from the Permian talk there as well, so if you can still come for those, you can also come. So I'll leave that up there if anybody wants to capture. And that's the end of the talk. 56 minutes. Good.
Yeah, good job.
Question or